In this experiment, we'll demonstrate how to use a bit comparator. So the aim of this experiment is to implement a 4-bit, a 5-bit and an 8-bit comparator using the given MSI, that is using the given IC. So bit comparators are again very commonly used in digital circuits. They are used to compare bits together, and depending on whether one bit is greater than the other or if both the bits are equal, we get a corresponding output. So when it comes to a 4-bit comparator, we have 8 inputs, and all these 8 inputs are grouped together as 4 pairs, and in each pair we have 2 bits which are each compared with each other. In a 5-bit comparator, we have 10 inputs, and in an 8-bit comparator, we have 16 inputs. We have to implement all these comparators using a single IC, that is IC7485, which is a 4-bit comparator. So the apparatus required again is a baseboard, the comparator IC, another IC, the XNOR gate, and a few jumper wires. So the procedure for this experiment is very similar to the previous experiments. You'll have to mount the IC in any one of the 10-pin sockets. Using the pin diagram, you'll have to find the VCC in the ground pins as well as the input and output pins. You have to connect the VCC to +5 and ground to the ground pins. And you can connect the input pins either to +5 or to ground, that is logic 1 or logic 0 depending on which case is being implemented. And for this IC, you'll have to carefully note which pins are those of cascading inputs and which of those are for the outputs, since we have 3 pins as cascading inputs and 3 pins as the outputs, and all 3 of them are labeled in a very similar way. You can connect the outputs to the LED box, and we have 3 outputs over here. These denote A greater than B, A less than B, or A equal to B, depending on what the magnitude of the data is. And you can vary the data on the input pins and observe the output that is produced. So over here is the circuit diagram for the 4-bit comparator. As you can see, we have 8 inputs over here, going from A0 to A3 and B0 to B3. So in this case, B0 will be compared to A0, B1 will be compared with A1, and so on. Here are the cascading inputs, which in this case will not be used, and here are the outputs, that is A less than B, A equal to B, and A greater than B, depending on what the magnitude of A and B is for that particular case. Then we move on to the 5-bit comparator. So over here we'll require 10 inputs. So in this case we'll have to use the cascading inputs over here. So since we are using only one IC for this, we'll have to use the 3 cascading input lines that we are using. So A greater than B is grouped with one of the input pins, and A less than B is grouped with another group. So this gives us a total of 5 bits as inputs. And on the output side, we'll have to connect an XNOR gate. And since the XNOR gate always gives us the output as 1 when both the inputs are 0, so we'll consider the output of XNOR gate as A equal to B. And then we have the third case where we implement an 8-bit comparator. So since the IC7485 is only a 4-bit comparator, we'll have to cascade two of them in order to give us an 8-bit comparator. So this is the first a 4-bit comparator. It has 8 inputs ranging from B0 to B3 and A0 to A3. So this becomes the first 4 inputs, and the second IC gives us the next 4 inputs, that is from B4 to B7 and A4 to A7. So over here again we'll make use of the cascaded inputs. So these will be the LSB inputs, and depending on the output that we get, we'll connect the output pins of this first IC to the cascading input pins of the second IC. And finally, we'll connect the output pins of the second IC to the LED box, and we can observe what outputs that we obtain for our particular test case. So here is the truth table for a 4-bit comparator. We start from comparing the MSB bits for a 4-bit comparator, that is A3 and B3. So in all of these first 7 to 8 cases, the cascading inputs are marked as don't care because we don't need them. So in this case, if A3 is greater than B3, the output, that is OA greater than B, should be high, and the other two outputs should be low. So on connecting these three outputs to the LED box, you will notice one of them is glowing and is logic 1, while the other two of them will not be glowing. And the second case, if we have B greater than A, so we'll have the output B greater than A that will be glowing, and the other two will be logic 0. Then we move on to the third case where A3 and B3 will be equal. So after this case, we start comparing the next MSB bits, that is A2 and B2, and we have two cases here again, that is A will either be greater or A will either be less, and in the third case we have both of them as equal. So once these two are equal and A3 and B3 are also equal, we can move on to the next pair of bits, that is A1 and B1. And similarly we can move on to the other case where we compare a naught and b naught, and for all these cases the cascading inputs will be 0, and the corresponding outputs will either be a greater than b or a less than b. And once we reach this case where all 8 of these inputs are equal, then we can start with using the cascading inputs as well. So in this case we'll have either the cascading input a greater than b as high, or we can have b greater than a as high, or we can have a equal to b, and correspondingly we will obtain the output, that is either a is equal to b, or a is less, or a is more than b. So you can verify the truth table using different test cases, and using these cascading inputs you can also implement the 5-bit comparator, and using both two of these ICs you can implement an 8-bit comparator. In the next part of this video, we'll demonstrate how to implement a 4-bit comparator on the mobile lab, and we'll also show how you can make the connections and how you can observe the output for various test cases.
In this part, we'll show the demonstration of how to connect a 4-bit comparator, that is the IC7485 on the mobile lab.
So to make the connections for 4-bit comparator, you must go through the pin diagram of IC7485 carefully, because the pin diagram are not similar as that of earlier ones. So the pin number here 16, it is connected to VCC, and pin number 8, again it is going to the ground. The 3 pins above the ground are nothing but our output pins. All the other pins on the right hand side are so these are nothing but our output pins, the 3 pins above the ground. So all the remaining 7 pins on the right hand side and 1 pin on the left hand side, which is the pin first pin, these are nothing but our input pins. So here you have completed all the connections for 4-bit comparator. And so after making connection, this is our circuit. So now let us verify the truth table. So we are considering the first case on the truth table, which is A3 greater than B3. So our red wire is A3 and B3 is white wire. So as A3 is greater, so A3 must be logic 1 and B3 must be logic 0. So in that condition our orange wire is 1, which is nothing but the pin number 5, which is O A greater than B. Now for the second case is nothing but A3 equal to B3 and A2 greater than B2. So the brown wire is our A2. So after making A2 high and all the other low, we can see that here only one is glowing, which is gray color, which is our pin number 7, which is nothing but OA greater than B. So now let us try the third case, which is A1 less than B1 and all the other are 0. So for that A1, so this black wire is nothing but our B1, so we are making it logic 1, and for here as well the gray wire is 1, which is nothing but OA greater than less than OB. Now go to the next case, which is AO greater than BO and all the other are 0 or basically equal. Let us try the next case, which is A0 greater than B0. So the gray wire here indicates the A0. Let us connect it to for this case, AO greater than B0, the output which is greater than OA less than B. So you can similarly verify all the other conditions given in the truth table. On verifying the 4-bit comparator, you can also try 5-bit and even 8-bit comparator.